So now we are starting our last lecture of the series, and Professor Sutton will be our speaker. Thank you very much for coming.
Good afternoon, everyone. Is my sound good? Yes. Good, thank you. Okay. Right. One more session, and then you're all free. I hope you've enjoyed the week as much as I have. I've been asked to end the summer school with a lecture looking ahead to future opportunities for science from the next generation of gravitational wave detectors. Now, we've had lots of great lectures about mainly about Einstein telescope and cosmic explorer over the last 2 days, and also on electromagnetic follow-up opportunities in multi-messenger astronomy. So I'm going to highlight, there's a lot of science that can be done with these instruments. I'm going to pick out a few of the things that I'm personally particularly interested in, and I'll try to provide references where you can find about the rest of the material. There's a lot of science to be done. And in a sense, I'm somewhat jealous of all of you here today. I joined the LIGO collaboration about 20 years ago, back in 2001. And for the first 15 years or so, there were no gravitational wave detections. It's fun work anyway, but it's been a lot more satisfying the last few years now that we started to see things. And I think you're in an excellent position because you're of the right age and career stage that if you want to pursue gravitational wave astronomy as your career, you're at the point where it's like the Wright brothers in the U.S., right? Have just taken flight at Kitty Hawk. When you're doing your PhDs and your postdocs and starting your faculty positions, right, we'll be flying properly at that point. So I think it's a very exciting time for you guys, and I'm going to highlight a few of the things that I think are going to happen over the next 15 to 25 years that will be particularly interesting, and I hope you find them interesting as well. So let me just start by just recapping some of the highlights of gravitational wave astronomy to date. So what's happened over the last 6 years or so, 6 or 7 years, since the first detections? Well, we've verified that gravitational waves exist, right? We've seen them. They seem consistent with general relativity. We've verified that merging black holes exist out there in the universe. They merge within a Hubble time. We've seen a lot of black holes, more than we expected. If you'd asked people on rate predictions, say 10 years ago, they probably wouldn't have, I think they wouldn't really have hoped to have as many binary black hole signals as we've seen in particular. So this is what's called the stellar graveyard plot, the binaries observed by LIGO Virgo to date. So we've seen this, but just to quickly remind you, the idea is for each of these vertical lines, that's a binary of this mass and that mass merging to give you a combined black hole of that mass. And so the blue are basically all of the black hole binary mergers we've seen. And then down here, we have lighter mass systems, neutron stars, and then the electromagnetically known black holes and neutron stars are here in the sort of pink and the yellow. So there are a lot of interesting things about this plot besides the number of black holes. One is that we're seeing systems at masses that we didn't expect, as well as the rates. So for example, we have the so-called mass gap down here, and we're seeing objects being created, or potentially members of binaries that are merged to form something heavier that are in this gap between about 3 and 5 solar masses where we didn't really expect to see compact objects. Too heavy to be a neutron star and too light, we think, for a black hole to form by ordinary means. So it's very interesting what's going on with objects like this one. There's also up around the sort of 60 to 80 solar mass region, we have lots of black holes being formed there. It turns out nature seems to like 30 solar mass black holes. We've seen in Eric's talk and other talks, there's a peak in the mass distribution around 30 solar masses. So 30 plus 30 gives 60. It's a very common end result. But there are also some mergers where the starting component, one of the two binaries, is in that region. And that's an interesting region for a black hole to exist because of the so-called pair instability supernova effect, where if you have a star that would expect to give you a black hole mass around there should actually totally disintegrate in a pair instability supernova. So we didn't expect to see black holes sort of around here either. And so there's stuff to be learned there. But this is just a first view of the sky, right? So there's a lot to be learned here. I'm going to discuss that a bit more. The other interesting thing, of course, we've seen binary neutron stars. So this is, of course, the Eris rendition of GW 170817. We've seen that neutron star binaries do merge within a Hubble time. We expected that based on observations of systems like the Hulse-Taylor binary pulsar, but it's good to see it in practice. And in particular, we've confirmed a long-held suspicion that those binary neutron star mergers are associated with short gamma ray bursts. They're progenitors of at least some of the short gamma ray bursts. This artist rendition I particularly like because you have this matter being thrown off in this ejecta, and I don't know if the artist deliberately made it gold-colored or if that's supposed to be physically motivated, but we know from 1708-17 that systems, these binary neutron star mergers, are responsible for probably a significant fraction of the heavy element production in the universe. So that's really cool, and there's our periodic table now where this bright gold color is the fraction due to merging neutron stars at best guess. So that's all fabulous. A last highlight I'll just mention is the measurement of the Hubble constant, again using 1708-17. So this is it's a fairly broad uncertainty range in our posterior for the Hubble constant. That's because we've just done a measurement with a single system, and it's hard to measure the distance to that binary system if you don't know the inclination very well. But it can be compared to the results from Planck and from supernova observations. And of course, there's this famous 5 sigma discrepancy between the two. And there's the hope that in the future, this gravitational wave type measurements can help resolve that discrepancy and figure out what's going on, because the systematics in the gravitational wave measurement are completely different from the systematics for the others. Okay, so those are all interesting science. If I just flip back quickly, this is really great stuff. But it's really just the beginning, right? If we look at this population, I mean, we don't know where these black holes all came from. So we've seen about 190, something like that. But we don't know where they came from. We don't understand these masses, some of these masses, right? So we've just had a first peek at the sky, but we haven't actually gathered enough science, enough data to really understand what's going on. So we're really just taking our first steps. And it's in the next few years, the next 15 years or so, and in the next generation of instruments that we're really going to be doing astronomy at, gravitational wave astronomy at the high precision, high statistics level, and really starting to nail down what's going on out there in the universe. So this is this plot shows, it's from the Cosmic Explorer proposal, horizon study, and Matt Evans showed it in his talk yesterday, where they divide the science into sort of 3 broad categories with subcategories. This is a list I've pulled out of various topics that will be addressed, right? So we've got multi-messenger astronomy that Marika talked about yesterday and today. With the number of systems we'll be detecting, we'll be studying, it's expected, thousands of kilonova from the 3rd generation instruments. We'll be able to do high-level statistics of binary merger systems. We'll be able to study, as we'll see, things like the neutron star equation of state by studying the disruption of neutron stars and mergers, and also post-merger signals from binary neutron star mergers. We'll be able to do that cosmology at very high precision, sort of 1% level Hubble constant measurements, measurements of the dark energy equation of state parameter. So there's a lot there. A very popular field in LIGO Virgo generally is testing general relativity. In particular, we've got, because you're colliding 2 black holes, 2 very strong field, strongest field objects in the universe, that allows you to test general relativity in the highly dynamic strong field regime, and we will have hundreds of thousands to millions of such signals over the next 20 years to do this work with. And that allows you to do things like testing the black hole no-hair theorem, trying to see if there really is a horizon or evidence for a lack of a horizon in some objects, which would be very interesting. So that takes you beyond sort of the standard model. There are opportunities to look for other effects beyond the standard model. For example, new fields. I'll talk a little bit about that later in the talk. And then possibly, hopefully, we may see something from stochastic. I expect we'll definitely see some amount of stochastic background, probably astrophysical. Possibly we'll see something exotic from, say, phase transitions in the early universe. The odds will be much better with the 3rd generation experiments. Okay, now this is far too much to talk about. I'm going to attempt to actually stick to time. I know I used all of my time, including questions last time. But since this is the last session, I'm hoping that we'll have time to actually discuss and ask questions. And since I can't cover everything, I'm just going to pick a couple that are interesting to me, as I said, and talk about those. If you want to read more, these are some excellent references. So we've seen this from Matt's talk and from the Einstein telescope talk. So these are basically science cases and roadmap documents. So I've put specific links here for the Cosmic Explorer. This one's for Einstein telescope. These two reviews generally cover third generation network as a whole. They're not ET or Cosmic Explorer specific. This is also an important one. This is one I mentioned in my talk. You see it's quite old. It's what's called Observing Scenarios paper. It's the LIGO-Virgo-Kagra collaboration paper that projects the operation of the current detectors in the coming years and what we've done. And that's actually important because LIGO and Virgo are still operating. We don't have ET and Cosmic Explorer yet. So actually the first science opportunities, future opportunities I want to talk about are the ones we're going to get from this guy, from LIGO-Virgo-Kagra. Okay, so you've seen this slide before, or some version of it. This is from that Observing Scenarios document. It's the plan for LIGO-Virgo-Kagra operations over to as far out as they're currently planned, right? We only go about 5 or 6 years into the future at a time. It's hard to plan clearly beyond that with any certainty. So this is the past. We are sort of right about here, mid 2022. So this is the latest published version of the document. The plan at the time was the next science run would start in middle of December of this year. That's now been pushed back to March 2023. So I don't have an updated version of the graphics, so I'll just put that correction in. But the point is that we will be operating the detectors with a projected sensitivity that is significantly better than the 03, as we saw from Lisa's talk. And then a couple of years later, we'll be upgrading to 05 and basically running slot more or less continuously for several years with occasional breaks. And the sort of A+ projected maximum sensitivity is really significantly larger, 325 megaparsecs versus around 130 to date. Now, you can actually do a lot with that, that factor of 2, 2.5. So let me start by just pointing out one thing we can do. I mentioned these binary evolution models. Where do all these black holes come from, right? Why do they have the masses they have? People have been modeling binary stellar evolution for decades. Eric showed a great plot, the upper limit plot from the end of the advanced LIGO era, the end of the initial LIGO era, where he showed these bands. They're about 3 orders of magnitude uncertainty in the predicted rates for black hole mergers, neutron star mergers, and neutron star black hole mergers. Because that's the state of the modeling. It turns out the astrophysics is very complicated and there's a lot unknown. So this is a really nice recent review. In this particular review, the authors look systematically at all of the main sources of uncertainty in current binary stellar evolution models. And they attempt to map out the range of what's possible with current understanding. So this is just a table I pulled from the paper. It lists 20 different parameters that they vary, right? 20 different values of main parameters. So there's 20 different values of numbers that are all very important for the evolution of the binary systems, for which we don't actually know the value. They combined this with a star formation rate density model. So, of course, how any given binary evolves depends on these numbers, but how many binaries you start with depends, of course, on the star formation rate. So they take a model for the star formation rate, and they vary the star formation versus redshift and metallicity. They try different metallicities for the galaxies and different initial mass functions for the galaxies. They wind up generating 560 copies of the universe, any one of which is possibly the one we live in, right, or close to the one we live in. So this plot at the bottom right, it's just one of the example plots in the paper. It shows the rate at which you form a binary neutron stars, neutron star binaries. The rate is per unit mass of the galaxy, and that's versus the metallicity, the content of the fraction of heavy metals in the galaxy, right, on the log scale. And so what you see, of course, there are a great many, versus metallicity, there's a great many different possibilities for the rates. And if you just read across, sort of the lowest rates, well, some of the rates appear to be approximately 0, but there are plausible rates down at 10 to the minus 7, up to 10 to the minus 5. So there's a 2 order of magnitude variation in the number of neutron star binaries you get, depending on what the universe has chosen for these values and for these values, these models. And we don't know, right? So what you need to solve this problem is data, is statistics. So here's the outlook going back to the Observing Scenarios paper. We've seen these plots before. Again, this is the noisy ones are the measured spectra for LIGO and Virgo to date, and then the smooth curves are the projected ones. And I just want to point out, if you go back up to that 2028 area at the end of my Observing Scenarios timeline, projected sensitivity of around 325, 330 megaparsecs. That number is specific to binary neutron star systems. It's an averaged range. But you can take it as a rough estimate of the overall sensitivity to anything, right? So the range for black holes will be different, but if this range goes up for BNS systems, it will also go for black holes. So what I want to do is just point at where we are with the current data set, the O3 data, the last data we've collected, maximum of 130 by this measure. 6 years from now, something like that, we're expected to be at 330. So that's a beta factor of 2.5. And so, I mean, it's a very quick, sorry, I should have shown that legend. Let me skip to the 2.5 calculation, right? So if I just take that ratio, that's about 2.5. You cube it, you get 16. What that means is that in a few years, the current detectors will be seeing about 16 times the volume of the universe. The detectors in 6 years will be seeing 16 times the volume of the universe as during a previous science run per unit time. So just quick scaling then. We had, I believe, 73 binary black hole detections in O3, plus or minus 1 or 2. So if I just scale that up, so that was approximately a year of data collecting. So I scale it by a factor of 16. I get to around 1,200 binary black hole detections per year when we're in the O5 stage. Binary neutron stars and SBH systems are a little more uncertain because we've detected 2 each of those in approximately 2 years of running over these 2 science runs. So if I just roughly say 1 per year at 100 megaparsecs-ish, you're certainly going to scale up to at least order 10, maybe 20 or 30 per year of these systems in O5. So there's a lot of science to come out of the LIGO-Virgo-Cogra network before we do any upgrades to ET. So let's see how that might work. This is another nice paper. It's a bit older, 2017, but in this study by Zevin et al., what they're trying to do is determine how many detections we need to go back and answer the question of which universe we live in. So they don't do as comprehensive a modeling as the more recent review of Blorgarten et al., but I just want to show what they have done. So what they've done here is they've divided up the scenarios to consider 2 different factors specifically, not all 20 parameters that can be varied, etc. So we don't know, we never have known, it's been uncertain, where black holes specifically, and that's what they're studying, where black holes are actually born. So the 2 main models that we've always talked about are so-called field binaries and cluster binaries. So field binaries, that means sort of ordinary binaries that just form out there in the galaxy, like any other stellar system, right? Stars are typically born in binary or multiple systems. If the 2 stars that form out of the cloud are high enough mass, they'll eventually form black holes. They're a binary, and maybe stellar evolution will allow them to merge within a Hubble time and give us a gravitational wave signal. And so those are the field binaries. The other option for where the binaries come from is from a dense stellar environment. So, for example, a globular cluster, and so these are called the cluster-formed. So in that case, you've got 2 black holes or neutron stars. They're born independently of each other in the cluster, but because of the fact that the cluster has a very high mass gradient, the heavy objects tend to fall to the center of those dense environments. And so 2, say, black holes that were born independently both migrate to the center and encounter each other and form a binary dynamically, sort of on the fly. So that's your cluster binaries. It's unknown what fraction of the signals we see come from these 2 scenarios. And so what they've done is they've taken those 2 possibilities. So they form a population of field binaries and they form a population of cluster binaries using some models. The other uncertainty they study is a so-called birth kick. So when a black hole forms from a supernova explosion, the supernova is expected to not be symmetric. There'll be some linear kick. So there'll be a net angular momentum imparted to the newborn black hole called the kick, and the black hole can get thrown. It's some additional velocity gets added onto it. If the kick is too large, it can throw the newborn black hole straight out of the binary, or otherwise just alter the binary configuration. And so we don't know exactly how big the kick is because the supernova explosion mechanism is not known with any certainty. So they consider 3 models. The fallback model assumes some amount of matter falls back into the black hole and dampens the kick. There's a proportional model where the kick depends on the mass ratio with the other companion, and then a full kick model where you get the maximum possible kick. So 3 kicks times 2 birthplaces give you 6 different models. And so for each model, they generate a population of black hole binaries. And so the horizontal axis in this distribution is the chirp mass. That's the quantity, remember, that we can measure really well with gravitational wave observations. We get the chirp mass really precisely, very easily. Well, relatively easily. For relatively low mass systems. And then the histogram is just normalized, so it sums to unity. And so what you see is depending on the size of the kick, that depends on, that affects how big these peaks are, and it also affects the overall shape, and you get different shapes and different peaks in the 6 systems. So that's the solid histogram. And then they've added, what they've done is they take this population for each one of these histograms, and that you've got now a simulation, so you've got some population, we've got a particular mass distribution and other binary properties. You can compare that to the detector noise spectra and say, what fraction of the systems sort of in this mass bin where that peak is, what fraction of those systems will be detected by LIGO Virgo? And it's that many. And then maybe over here you've got, at high masses, you've got maybe relatively fewer systems, but those have much stronger gravitational wave emission. So if you count what fraction of those are detected by LIGO Virgo, it's a much larger fraction relative to the lower mass. And so this solid line without the fill is the same distribution after you apply the selection effect of which ones are going to be detected by LIGO Virgo on average. So the general scenario is that what happens is you shift the distribution of the peak towards higher masses, and that's just because we can detect higher mass systems further away, so they're easier to see. Okay, so their simulation population, 1, 2, 3, 4, 5, 6. They've got 6 populations of these final results, these solid lines, are the predicted observations of LIGO Virgo. So now you can say, okay, let's collect data from LIGO Virgo for n years and make the histogram of what we detect and try to match to these 6 histograms, right? And see which one, see if you can determine which model is the right one. So I'll just show one result from their paper. I'm sorry, it's quite blurry, but it's this is how your accuracy on measurement varies with the number of detections. So the vertical axis, it's 6 different scenarios for the fraction of binaries that are in the field versus the fraction that are in the born-in clusters. So they call this in the paper beta. So specifically, beta is the fraction that were born in globular clusters or other dense stellar environments. And so they go, so we've got beta 1 to 0. So it's sort of 6 different universes, right? And then as you move across, it's the 3 different fallback scenarios. So they test for each universe, each fallback scenario, you make your population, and then you measure, on the horizontal axis is the number of observations you have, and then the bands are your posterior measurement of that beta parameter. So basically what it means, so if you only have here, at the left-hand edge, I'll just look at this plot, I've got 10 observed black hole binaries. If beta is equal to 1, then I'm only going to be able to, that's again the fraction in clusters versus field, I'm only going to be able to measure that with a sort of a 1 sigma uncertainty that's somewhere between 0.5 and 1. So really not very well at all, right? Sort of 100% uncertainty. By the time I get up to 100 observations, actually, that uncertainty range, my credible interval, is now down to around 0.1 or 0.2 in thickness. It's much narrower. And if I get up to 1,000 binaries, I'm down at the few percent level. So the upshot is that if I get if I go from 10 detections to 100 detections up to 1,000 detections, I can start to tell the difference between which of these histograms I'm actually observing with statistical confidence, right? And so they cut off their counts at 1,000, but you can see in each case at 1,000 observations of black holes, you're at the several percent level precision for figuring out that ratio of cluster versus field. And so similar, you can do similar then to try to determine the natal kink. So I'll leave that. But again, before the ET and CE turn on, again, we expect of order 1,000 black hole detections per year of observing time. So we will be able to nail these properties down before the next generation of detectors turn on. I think that's interesting. You're actually doing concrete astrophysics where you're really saying something about how the nitty-gritty of how the universe works. I'm just going to take a gamble based on the questions that we've had so far, that bit is probably the least interesting thing we could do with gravitational wave detectors for you guys. Maybe I'm wrong, but a lot of the questions that we've had have to do with things like alternative gravity or alternatives to the standard model and so on. So I'll talk about 1 or 2 things that are a bit more exotic now. We've been asked a couple times about stochastic gravitational wave backgrounds, and this plot, or a version of this plot, got flashed in one of the earlier talks. It shows. So this number omega GW is the energy density in gravitational waves as a ratio to the total energy density you need to close the universe. Okay? So basically, if we were at, if you had enough gravitational waves to close the universe, you'd be at 1, which would be up here somewhere. And then these are predictions from various models, right, of how you might produce, various things that might produce a gravitational wave background. And then you see some curves here from cosmic microwave background observations or advanced LIGO observations, where we're able to put limits in some frequency bands. So in particular, for the LIGO Virgo ground-based detectors, we're sensitive at around 10 to 100 hertz. And so we've got this narrow band in limit. It will get better with the advanced detectors, and then we've superimposed, by coincidence, of course, in that same frequency range, various models of, say, a phase transition in the early universe, or cosmic strings, this gray band that could possibly, the black line, various things that could possibly give you a stochastic gravitational wave background to detect with these limits. And so the 3G goes well down, several orders of magnitude past the advanced detectors. I'm actually not interested in the 3G detection of the stochastic gravitational wave background, because this is a result from a recent LIGO paper, the O3 analysis of LIGO Virgo data for stochastic gravitational wave backgrounds. We have this population of all these black holes out there. Yeah, there are a lot of them, and more than we expected, again, 10 years ago. Those will produce their own astrophysical background of stochastic background of gravitational waves, right? Because you've got, for all the ones we see, there are many, many more that are a bit further away, that are unresolved in the data, and just appears a weak background hiss. And so the left plot shows our current estimates based on detection rates of binaries of how much stochastic gravitational wave background there should be, just due to the things we've detected. So the green curve, the best constrained one is BBH, because we have, again, about 90 detections. So we have some reasonable handle on how much the stochastic background should be due to those, that black hole system, those black holes. We don't know precisely, because we don't know the exact mass distribution. We just have estimates. And then the red curve is much more uncertain, but that's the background from binary neutron stars. We've only got 2 of those, so the statistics are much poorer. So in the paper, we claim we don't have enough information from the putative black hole neutron star detections to put a firm prediction for that. So there's just an upper limit. But if you sum these, you just transfer over to the right-hand plot. So this blue curve is the median or best guessed estimate of the stochastic background we'll expect from all the binary systems that the sort we're detecting now, plus a shaded band that shows a 1 sigma uncertainty region. This dashed blue line is sort of the upper limit if you really push the black hole neutron star binaries to the limit. And then these curves are the projections, right? So we've got the O2 result and the O3 result. The initial design result isn't quite low enough, but the A+ design, the sort of O5 era design, if we reach that performance, it should be low enough that it's actually cutting into this band. So there's actually a pretty reasonable probability that we will detect a stochastic gravitational wave background in the coming decade, basically. It's not as exciting as the cosmological background, because this is from sources that we already know about, right? That we know about this population, but it is quite cool, I think. Okay, so attempt to stay on time. I want to go back to cosmology, and we're going to jump over to the 3rd generation instruments here. So just again, I remind you of this plot. This is the Hubble diagram. The posterior on the Hubble constant diagram from the 1708-17 measurement. And I'll just point at, we've got this 5 sigma tension. I'm sorry, that's supposed to be a sigma rather than an S. A 5 sigma tension between the existing results from electromagnetic astronomy. The next generation detectors, of course, are going to have much better statistics. There we go. So this is a beautiful image. I believe Matt credited Evan Hall with this. This really makes the point. To do precision cosmology with gravitational waves, you need high statistics. And I mean, the rationale, I think, is simple enough. As Marika explained, you need to know the inclination angle. Well, you want to know the inclination angle of the binary. Right? If it's pointing directly at you, the gravitational wave emission is stronger. If it's pointing away from you, the gravitational wave emission is weaker, some factor of 2-ish. And so not knowing and it turns out that measuring the inclination directly from the gravitational waves is hard. So as a rule of thumb, there's sort of a factor of 2 distance uncertainty you get from a typical binary just from not being able to resolve the inclination very well. And factors of 2, again, go back, you don't want factors of 2 in your distance. That's basically where this width is coming from. So to beat that down, you need statistics. You need a lot of observations. So it's expected here that the 3rd generation network will see of order 1,000 kilonovae, for example. So binaries with electromagnetic counterparts. And it's probably not surprising to this sort of diagram. So as Matt explained yesterday, the yellow dots are sort of a best guess distribution of all the neutron star mergers in the universe, and the Einstein telescope and Cosmic Explorer, right, we'll be able to see it to approximately these distances, which means we'll see pretty much the entire population. And they're at a redshift that's interesting enough. So our current observations, 170817, that's at a 40 megaparsecs, which is a redshift of 0.01, something like that. So you need to be able to measure binary systems at a redshift of order 1 to do cosmology well. And we'll be able to do that. So this diagram is specific for the black hole case. You can do this similar statistics with enough black hole detections and comparing to large-scale structure and galaxy catalogs. But even if I just take sort of the 5 solar mass limit down here, which is close to binary neutron stars, you see that we're getting SNRs of 10 and 20 still out to a redshift of a couple. So you can see out to from here out to redshift of 2, you'll still be able to detect these systems. And because of the sheer number, you will get those counterparts you need to do things like Hubble observation measurements and cosmology. So I wanted to show this plot from this paper. This is a really nice one. It's in the I think it's in the ET design study document. This is the original reference. So this shows a result of what you can do with ET and 1,000 standard sirens to constrain the cosmology of the universe. So specifically, the plot shows here omega m, that's the energy, the density of matter, baryonic and dark matter in the universe, on this 0 to 1 scale, where 1 is the closure density for the universe. And then omega naught is the dark energy parameter. So if the cosmological constant, that dark energy we see, if it is just a cosmological constant, like in general relativity with the lambda term, then the value would be -1, this parameter of a value of -1. If it varies away from that, then you've got some sort of dark energy that's not just a straight cosmological constant. So for the simulation result, what the authors did is they generated 1,000 standard sirens, which is a reasonable number to expect from the Einstein telescope observations, ET observations alone. And then for each one, you can do this game where you attempt to estimate the distance and use it to constrain the cosmological model that you're in. So for this specific calculation, they assumed that we're at sort of the standard cosmology where the true value of omega is about 0.3, of omega m is about 0.3, and the true value of the dark energy parameter is -1. So that the real universe is right there in their simulation. And then they show what happens. So we already have obviously we have lots of interesting constraints on cosmology from cosmic microwave background and other observations, supernova, baryonic acoustic oscillations. So those sort of pre-existing constraints are here in the red. Yeah? So that's what astronomers can do. And so why do we need gravitational waves for that? Well, the gravitational wave standard siren measurement gives you this really large gray banana. And that doesn't look very impressive on its own because the gravitational wave observations are much less powerful than electromagnetic constraints. But the interesting thing, whenever you do a parameter estimation problem or data analysis problem, is to look at the correlations or degeneracies between your parameters. So if you look at the red curve, which is our electromagnetic data, right? So they're able to constrain very well in this direction. They're not very certain what's going on in this direction. The constraints from gravitational waves are almost at 90 degrees. So we're really crap at this direction, which is roughly the direction in which electromagnetics work very well. Thank you. But we're much better in the direction where electromagnetics is not very good, right? We're very good relatively good in this direction. So again, this width is about the same width as the red ellipse, but when you multiply the two probabilities together, you do decrease it quite a bit. And so we get down to this blue ellipse if we combine both the gray gravitational wave and the red electromagnetic observations. And so you're decreasing by, it looks a factor of 2 or 3 at least, your uncertainty in where in the universe, where our universe lives in this diagram. So that's cool stuff. For some reason, my slides aren't advancing every time I tap. Okay, here we go. Yes, 10 minutes, good. So I will run a little over time, sorry, but this stuff is kind of cool, I think. So another topic I just wanted to touch on briefly is post-merger, determining the neutron star equation of state, specifically post-merger gravitational wave signals. So if 2 black holes merge, it's kind of boring. You just get a black hole. But if 2 neutrons, it's still cool, but it's not as cool as if you take 2 neutron stars and merge them. If the neutron stars are low enough mass and you have enough angular momentum in the system, it's possible, depending on the equation of state, how stiff the neutron stars are, you may get what's called a hypermassive neutron star, a single large deformed neutron star that is, so typically it's supported against gravitational collapse by its very high angular momentum. Typically these things are short-lived. They may spin down and then collapse to a black hole, but the exact behavior depends on, again, on the equation state, which we do not know. So this is your black hole signal, very boring. This is the corresponding signal for a neutron-star merger for various equations of state, right? So you have that same in-spiral, peaks at a merger, and then instead of just ringing down quietly, the hypermassive neutron star stubbornly stays alive for anywhere between maybe 10 and 100 milliseconds. But it's spinning very, very fast. You're at a couple of kilohertz frequency here. And so you get this, you get this very high frequency gravitational wave emission. Again, the decay, whether or not it decays in amplitude, depends on the equation of state. But typically they may decay or they may stay relatively stable until collapse. But the morphology depends on that equation of state. So this is a plot from a paper by, again, apologies for the, sometimes when I put the plots in, they come in at low resolution. I'm not sure why. So this is a paper by Sutton et al. From PRL from a few years ago where they were looking at this in a little more detail. So this plot just shows examples for 4 different equations of state. And they've transformed from the time series to the frequency domain here. So the dark lines you can see, the dark jagged lines are the Fourier spectra of these post-merger signals. And if you peer in detail, a typical characteristic is that you have basically characteristic frequencies in here, right? You have these peaks F1, F2 for each one. But the exact frequency of those peaks depends on the equation of state. So here it's about 2.4 kilohertz maybe, here it's about 3.1 kilohertz. So if you can detect the post-merger gravitational wave signal, it's actually pretty easy to measure the frequency of a sine wave in your data. That's just about the easiest data analysis problem you can solve. So if this signal has a high enough SNR to stand it above the noise, it's fairly easy to measure those peak frequencies, and then you compare it to the equations of state and constrain those. These smooth lines here in green and in blue are projections. It's a way to measure how the noise spectrum of the detectors matches against the signal. They're using a kind of non-standard unit here. So this is the advanced LIGO noise curve compared to the post-merger signal, and this is the ET noise curve. To translate into numbers, this height of curve above this, the height of signal above this curve translates into SNR of order 1 or maybe 2 at 100 megaparsecs using the LIGO design. But then if you drop to ET, which is about a factor of 10 better at these frequencies, you're getting 10 or 20 SNR for a signal at 100 megaparsecs. And 100 megaparsecs is where we expect to see signals at some reasonable rate, at least a few, of order 1 per year. So, and in principle, by taking many binaries that are even further away at low SNRs, you can stack them and look to see if there's a peak. Since all of the neutron stars should be under the same equation of state, you could take many weak signals that have a peak here and stack them to build that peak up. And so they estimate the ability of Einstein telescope to determine the equation of state. It's an interesting paper. Okay, I tried to promise to stay in time. According to my clock, I've got 7.5 minutes to do that. But I wanted to go a little bit off the beaten path. Everything I've said here is something you've probably heard before or got briefly mentioned in one of the previous talks. So I wanted to pick a couple of things that I thought might appeal to you guys, just based on the questions. And so I wanted to look at 2 examples of going beyond the standard model. These are of particular interest to me because I've actually dabbled a little bit in these projects myself. So the first one is something called domain walls. And I don't think I've seen it mentioned in any of the reference documents yet, but it's a cool topic. So what is a domain wall? So here I'm going to get a little more technical because I think it's worth explaining a little bit of the math here. It's fairly simple. So the idea is, we suppose there's an unknown field, say a scalar field out there everywhere in the universe that we haven't detected yet. This is a potential model for the dark matter, right? Well, what is that dark matter that comprises sort of 26% of the energy closure energy density of the universe? So let's suppose, for sake of hypothesis, that we've got a real scalar field that we haven't yet detected, and it's got one of these sort of Mexican hat-like potentials, right? It's got a potential that looks like this. So, a very simple model. Phi squared, a minus phi squared term and a plus phi to the 4th term will generically give you a shape like this. The exact shape doesn't matter. It's that you've got 2 minima. That's the key thing. So in the early universe, everything's hot. The field has lots of energy, and so you can basically, in terms of field value, you've got sort of this level of energy, so the field can take any value it wants anywhere in the universe. That's fine. But as the early universe cools, well, your energy level drops, and you eventually hit this barrier here, this peak. And so you either have to fall on that side to get cold, or fall on that side to get cold. So at any given point in the universe, that scalar field, if it has this sort of potential with double minima, it's going to has to make a choice when it cools whether it's going to settle into, say, the negative state or the positive state. Eta is just the value at that minimum, just some constant that we don't know. Right. Okay, so why is this interesting? Because this gives you what's called the domain wall. So the idea is, this is some large patch of the universe, and different regions here are outside of causal contact with each other when the cooling happens, and when the scalar field has to make its choice about which positive or negative vacuum state it's going to fall in. So some regions are going to fall into the negative, and others are going to fall into the positive. Okay, well, that's got to happen because they can't all coordinate and all decide to fall into the same one. And so if you go back to that potential energy diagram, the green area, right, that's where I'm transitioning from minus to plus, from plus back to minus. That means my field has to be transitioning through zero, the zero value. But if you're transitioning through that zero value, it means you've got a non-zero total potential. So those green barriers, green lines where we're transitioning between the two regions, have a non-zero energy density, right? And that's what's called the domain wall. It's just a wall of energy in this scalar field. Okay, so why is that interesting for LIGO? Well, the thing is, these domain walls can have a physical effect. They do have a physical effect. If one of them passed through the Earth right now, it would have some effect on us. The exact effect depends on how that scalar field phi couples to matter and couples to photons. So there's a nice paper by my colleague Hartmut Grote at Cardiff and a colleague of his in Germany. They wrote a couple of years ago where they worked out the physical effect under various assumptions of that interaction. So I'm going to do what's called the quadratic interaction case here. So one possibility, in the simplest case, is that when that scalar field passes through, the scalar field affects the masses of fermions. So instead of having the mass we expect to have, the mass is shifted by the field value divided by some coupling constant. We don't know what the coupling constant is, but it just describes the strength by which that field couples into matter. And so this has a neat effect. So if I go over to the diagram, it's going to cause matter to accelerate. You get, if the mass of the object, if one of those domain walls passes through, it means your field value is changing, right? Which means that this phi value is changing, so your mass is changing. And in the paper, they show that the change in the mass of your object, your particle, produces an acceleration. Basically, particles fall into domain walls when a domain wall gets close. So this is the field value, where we go from, say, the positive vacuum down to the negative vacuum, and this is the square of the field value, which tells you what your energy intensity is. And you'll find that the acceleration, basically, if you have a particle on the left side, it's going to fall in the positive direction. A particle on the right side will fall in the negative direction. They fall into the walls. Now, imagine my test particles are the two mirrors of a LIGO detector. What that means is if one of these walls passes through LIGO or Virgo, when it hits the mirror is going to fall into the wall and fall away from the other mirror down there that the wall hasn't reached yet. So this could produce a detectable signal. This is really cool, I think, because gravitational wave detectors, LIGO, Virgo, Kagra, we think of them as devices for detecting gravitational waves. And they are devices for detecting gravitational waves. But that's not all they are. They're actually, what they really are devices that measure differential motion, right? Differential displacements. So gravitational waves can produce that, but they're not the only thing that can produce that, right? Effects like domain walls can produce that. So you can use the same instruments to measure phenomena that are completely unrelated to gravity, which is kind of cool. And this is the one example. So when I made these slides, I was in sort of a cartoon phase. So this is my cartoon interferometer. This is one of my domain walls, and it's just coming right down the x-arm. What will happen, the green wall, when it hits this mirror first. The mirror falls into the wall when the wall gets close. And so what happens is the x-arm stretches a little bit when the wall hits. And then the wall passes through. When it passes through this mirror falls to the right as well, by the same amount the first mirror fell. And so now this arm is the same length as it used to be. This arm is unaffected because you're coming in at a right angle. Yeah, the mirrors move sideways, but there's no length change. And so what happens is that the green wall makes this green trace in your detector, which goes just a step function. Exactly how sharp the function is depends on how thick that wall is and how fast it's moving when it hits the mirror, right? How long it takes to cross the mirror. A wall coming from the 90-degree angle does the same thing, except it stretches the y-arm rather than the x. And because we're doing a differential measurement, if you stretch the y-arm instead of the x-arm, you get a minus strain signal. And so you get an identical signal with a minus sign. So what's kind of neat is the signal has the unusual property, because it's not a gravitational wave, that the morphology, the shape of the signal, depends on what angle you're hitting the detectors at. So even a single detector, if you could see one of these with a single detector, you could infer some information, basically the angle of the wall hitting the arms. Here's just another example. If you come in at some funny angle, you get a mix of the positive x arm stretching and then a smaller positive y arm, or negative y arm stretching, so you can get some funny shape like this. Or if you come in from sort of the backside, you can get these funny shapes where you get something like a sawtooth or these shapes. It all just depends on the direction. It's just a simple function of the geometry. It's very cool. So we can look for these. In the paper by Hartmut and his colleague, they projected what we can do in terms of setting limits on the domain wall coupling constant. This lambda parameter, that is the one that determines how strongly the domain wall couples the matter. If that constant is really, really large, then it's a weak coupling and we can't see anything. And so the limits we expect to be able to set depend on how sensitive our detectors are, right? The smaller the strain amplitude, the smaller the displacements, that's good. But the most important parameter is actually the distance, the thickness, the thickness of the walls. If the wall is really, really thin, it'll hit one mirror without touching the other. If the wall is, say, 1 meter thick, it'll pass through one mirror but not be affecting the other mirror 4 kilometers away. And then it hits the other mirror, and you get these nice sharp transitions. If the wall is, say, 10 kilometers thick, then it's still affecting the first mirror when it's also hitting the second mirror. And so really thick walls, once you're over a couple of kilometers in thickness, basically that wall will move both mirrors of the detector at the same way, and you get no signal. So we have sensitivity to a particular range of thicknesses of domain walls. And these projections are basically limits we can set on the coupling as a function of the unknown wall thickness for different detectors. Basically, the current generation of detectors are here, and you can see also LISA could also be used to do set limits. Because LISA is 1 million kilometers or 2.5 million kilometers in size, you can see much thicker walls with LISA. But the interesting thing is, of course, you can compare to existing bounds. So the shaded astrophysical bounds and clock bounds are what we can already set, limits already set with experimental data. So we can go, in these bands, sort of 5, 6, 7 orders of magnitude deeper limits with gravitational waves, which I think is really, really neat, because this has actually nothing to do with, we can set the limits of gravitational wave detectors, even though this signal has nothing to do with gravitational waves whatsoever. Very quickly say, I mentioned that I've been working on this. Actually, Hartmut and myself and a postdoc now, actually, Honki, who's starting a faculty position at Queen Mary University in January. We're working together to actually analyze the existing LIGO data to look for these signatures. So I'll just flash very quickly that the typical wall speeds are expected to be at 300 kilometers per second. That's just set by the dark matter halo, right? If these are dark matter objects. That's a typical speed of objects around our portion of the galaxy. So that means we have this interesting coincidence windows for the Hanford Livingston Virgo network. Instead of being 10 milliseconds delays, we're talking about 10-second delays or 30-second delays as typical. The signals can be very, very simple pulses, which could be very difficult, of course, to distinguish from glitches of, you'll remember how I harped on about this during my talk. We have lots of simple pulses, blips and things that look a lot like these, that will make the search a bit of a pain in the, well, a bit difficult to do, but we are doing it. The basic idea I'll just highlight, we're doing a cross-correlation analysis. So we just take short snippets of the data of order, we use different durations for different wall speeds and thicknesses, but you can take the idea of, say, a 10 millisecond segments of data and cross-correlating them with 10 millisecond segments in the other data at delays of order 10 to 30 milliseconds. A nice thing about this, besides being sensitive to domain walls, in principle, we might detect some other exotic thing that causes correlations between the detectors, right? Anything that travels at less than the speed of light, at sort of 300 kilometers per second or so, are things we could detect. And the papers in preparation, I will just say, it's not entire fantasy. This is one of the low quality detection efficiency plots that are put by the pipeline that we're using to do the analysis. The amplitude is sort of arbitrary units, but it demonstrates that if we put in large enough amplitude walls, we do detect them with good efficiency. So keep an eye out for that in the next month or two. Right. Just hit time, so I will talk briefly about one other cool thing. This is mentioned in some of the science case documents. I wanted to bring it up. It's the idea of black hole echoes. I've included this because I had a conversation with a couple of you over lunch, I think yesterday, about this, and there was a lot of interest on the possibility of these, again, beyond standard model physics. So again, I'm recycling some old slides, but hopefully they'll do. So this is an image from a paper by Abadi et al. It's an interesting and somewhat controversial paper, I think, where they're exploring the possibility, they're using public data from LIGO and Virgo to explore the possibility that the things we're detecting are not actually black holes. So there are lots of things that have been proposed as alternative exotic, what are called exotic compact objects, and there's a really nice living reviews and relativity article by Cardoso and Pani on this. So there's all kinds of possible theories for exotic objects that are not a black hole, so that don't have an event horizon. The nature of the object for this purpose doesn't matter. It just matters that the object is the size of a black hole but doesn't have a horizon. And so what happens if you take two of these objects and you merge them? So the gravitational wave emission basically looks like, if they're very, very close to black hole in size, then the gravitational wave emission will be indistinguishable potentially from a black hole merger, at least the main emission. But when that single merged object forms, it doesn't have an event horizon. And that's really important because it means you can get additional gravitational wave signal out of that merged object. So this diagram explains how the system works and why they call it an echo. So the idea is sort of at early times down here, just off diagram, the two objects merge and you have your standard in-spiral signal. You have an in-spiral merger and ring down. And this dashed line is going off to infinity, right? R versus T. That's the merger, that peak merger and ring down signal that we see at infinity, and we say, okay, we've just seen a BBH event. Now, but that object in this scenario isn't a black hole, so it doesn't have an event horizon. So what's happening? Well, when the object merges, the space-time just around it is kind of, it's sloshing wildly, right? It's in a standard GR scenario, those oscillations are the ring down, and the system settles down to stationary Kerr geometry. But that sloshing, waves have two components. You've got the outgoing component, which is the ring down we see, and you've got the ingoing component, which falls into the black hole and we don't care about. But in this scenario, that object isn't a black hole. So the ring down, that ingoing wave, can pass through the object and come out the other side and go off to infinity to an observer over there. Or in some scenarios, such as the fireball scenario, you may not have, instead of having an event horizon, you have some sort of barrier, a few Planck lengths outside that acts as a reflective membrane, in which case the ingoing wave bounces off of that and goes directly back out again. Doesn't really matter which scenario is the right one, if either. The point is, if you don't have an event horizon, those ingoing ring down waves that normally get swallowed will actually make it out to infinity, or some fraction can make it out to infinity. And so what will happen is that after your merger, those ingoing waves that are supposed to be swallowed bounce off of your firewall or whatever and come back out. And so you see an echo at some time later, an echo of the ring down signal. Yeah? A little more detail, you've got an angular momentum barrier right outside of the black hole, the Kerr geometry, you've got a curved geometry obviously, so that outgoing wave can scatter off of the geometry. So in general, that outgoing echo ring down, only some of it will be transmitted. Some fraction will get reflected back in towards the central object. That reflection can then bounce off the central object, come back out, hit that barrier again, some fraction transmitted, some fraction reflected back in. And so you get, in this situation, an echo. After the merger, at some fixed time, you get an echo that basically is the ring down, an echo of the ring down, and then that gets repeated at fixed steps in time. And it's a generic prediction, doesn't matter sort of what crazy model you've put here, roughly speaking. You expect that. So from a data analysis standpoint, this is great, because that's an easy thing to look for. You don't have to know the details of the theory, you're just looking for a repeated signal that's an echo of your original ring down. So this is an example from one of the papers. A number of people have now followed up this idea looking at LIGO Virgo data for echoes. This is just an example of what that signal might look like. So you've got the standard binary black hole merger and ring down, and then at some time later you've got an echo, and then another time you've got a weaker copy of that echo and a weaker and a weaker and a weaker. So the amplitude of the initial echo is not known, and the rate at which it decays depends on the parameters of your model. But what is basically fixed is the repeat time between the delays. And that's because that repeat time is just fixed by the Kerr geometry between your horizon and the angular momentum barrier. How long it takes the outgoing wave to hit the angular momentum barrier, bounce off, come back to the horizon, go back out again, that round trip time. So basically it just depends on your black hole mass and spin. And it's well defined. So for massive black holes, it's a large fraction of a second. Right? So this is, I think, worked out for approximately the mass of 150914. So it's a cool thing. I'll skip over some of the uncertainties since that's not terribly interesting. It's a cool idea, and the reason it got a lot of attention because that original paper by Abedi et al. Claimed a detection. Well, they claimed a sort of 1% false alarm probability event. This is a plot from their paper showing the SNR that they're reconstructing, and so of course a lot of people have followed it up. I won't go through all of them. I'll just flash a few. So we've got people using. So the original paper used a matched filter search. They constructed a waveform template based on this sort of model and did the filtering. Other people have done simpler analyses, sort of more model agnostic, where you make a time frequency mapping, you just fold it and look for power buildup. So other authors have claimed sort of 1% level detections as well, although with different values, right? Which is interesting. Just one more. Again, there was an analysis of the binary neutron star 170817 by Abedi and Ashforty. Again, using this folded spectrogram. Using the folded spectrogram approach, and they again claim to find echoes. So this is a plot from their paper. What they've done. So essentially, you've got the binary in spiral signal here, which is the real gravitational wave that we all believe, and then they fold the spectrogram according to the echo time they expect, and so they sort of scale and add the spectrogram, so 10 times. So this stuff down here is just rubbish. It's just it's just folded copies of the original signal. So this is not interesting. But what's interesting is, I'll warn you, they put the time axis going vertically. About a second after the in-spiral ends with a merger, they get a dots. So a series of dots at the same time. This one is the loudest one by far. That they claim to be an echo signal from this event. So in the unfolded map, basically, there's nothing there. But when you fold, it builds up a suspiciously large amount of power, according to their analysis. So, okay, very quickly, lots of people have followed this up and found nothing. I've done some tests as well for the BNS event using my own analysis. Didn't find anything. These are some p-values from a paper by one of the follow-ups. Right, these p-values, basically the probability that the event you see could be generated just by background noise, right? And they're all in the null hypothesis. Those are uniform on 0 to 1. These are all pretty uniform on 0 to 1. So it remains sort of controversial or unsettled. What I want to point out about this is to me a very interesting aspect. It demonstrates that we're starting to turn into, I would say, a real astronomical tool for discovery, the LIGO-Virgo-Cagra network. And what I mean by that, it's not just LIGO and Virgo using LIGO-Virgo data to make LIGO-Virgo papers. We've got something like half a dozen papers here over the course of 2 years of other groups outside of the collaborations using our data to try to find new things, new ideas that we hadn't thought of doing in the collaborations, and arguing over, getting different results and fighting it out like proper scientists should in the literature, which I think is really great. And you guys are going to be in this situation. I'm old enough that most of the publications I've been on were made by the Mammoth collaboration, where we all agreed on what to say, and nobody else really goes through the data the way we do. And so we tend to be authoritative. I think you'll be in the scenario where there's a lot of interesting high-sensitivity data being made public, and if you're interested in doing the analyses, you can do these sorts of tests and come up with your own, test your own theories and come up with really cool results, potentially, and have proper academic debates. It's really interesting and refreshing to see this going on. The answer for settling this, of course, is just more data. So we'll have those 1,200 BBH detections-ish per year in the next few years. By the end of the decade, ET and Cosmic Explorer will provide us with 1 million binary black hole mergers. So we'll settle the question of whether there are echoes or not. But I think this is another second interesting example of how you can go a little bit left field with gravitational wave data and look for stuff that's not sort of the standard thing, the standard expectation. It's really interesting science. So I failed miserably. I'm at 58 minutes when I was trying to stick to 45, so I apologize for that. But it still leaves some time to discuss. So again, there's a lot of stuff to talk about, and I'm happy to talk as well as I can about any of it. I want to flash this as a sort of a prompt of possible topics. But before we go to the question and answer session, I just wanted to say, I speak on behalf of all the lecturers. It's been a real pleasure being here. This has been a fabulous way to end 3 years of lockdown. This is my first sort of in-person meeting, and I've really, really enjoyed the talks and the discussions with all of you. I really want to thank Barry for inviting me to be one of the lecturers. I want to thank Professor Johannes for his efforts in organizing all of this. And I think we all should thank Eleftheria as well for keeping us all safe and keeping everything together over the past week. So if we could have a round of applause for the organizers. Okay. So, officially, I think it's 15 minutes, but I guess we've got as much time as you all have. So, I'm going to invite questions on anything I've talked about, but also I think we have a fair fraction of the lecturers here. So, since this is the last session, I think you should feel free to ask about any of the topics we've covered this week, and I will pick on my fellow lecturers as need be. Yes.
Thanks again for another amazing talk. I wanted to ask about the echoes. Could we just go back to the standard model, and is there a possibility that these come from, for example, MACHOs, massive compact halo objects as dark matter candidates?
So, MACHOs, massive compact halo objects. One possibility, for example, would be like just ordinary black hole binaries, primordial black hole binaries, for example. If it is just ordinary GR binaries, then of course you won't get echoes. But there's no reason why those objects, if they exist, could not be. I'm not aware of any reason why they couldn't be MACHOs, for example, a component of the dark matter. Yeah. So yes.
Thank you.
Thank you, Professor. Do domain walls sort of explain the large-scale structure of the universe in terms of an explanation for dark matter? And do they also somehow replicate the halo structure in galaxy formations and such?
Yeah, that's a good question. I'll admit you've gone beyond my level of competence. I don't think they do. In these limits, here, the limit that was projected here assumes that the domain walls constitute 100% of the dark matter. So to get to figure out the best possible limit, you assume they're 100% of the dark matter, and then that tells you the limit on this coupling. If they're 1% of the dark matter, then your limit is correspondingly weaker. I don't believe that 100% dark matter from domain walls would be consistent with cosmological simulations, but I'd be happy to be corrected if anyone in the audience knows better.
Okay, thank you, Professor. And
thank you.
And I have one more question regarding the signals between the domain walls and the echoes.
Yeah.
Just a technicality, like what is the ratio between the echo, for example, and the actual signal of the strain that we have?
Yeah, so echoes were this way, weren't they?
In terms of the amplitudes.
Yeah. So the key thing is, I think the key thing is, this factor A, as Westwick et al. Called it, just the ratio between the peak sort of standard gravitational wave merger signal amplitude and the peak of the echo. The size of that amplitude scaling factor is unknown. It's going to depend on your model. What model you put for the exotic compact object. So from a phenomenological standpoint, what we do is, what you would do is you take all the binary merger signals you could find. You know this time gap based on, you estimate it based on your assumed mass and spin parameters for the final black hole, and then you stack them. So you add up a lot of, in potential, the best way to do it would be to add up many signals. So you're adding up many echoes, but also from many separate black hole binaries. And the more you can stack, in principle, the smaller this ratio you could constrain or detect. But what nature produces, it might be zero in nature, or it may be very, very small.
Okay, thank you, Professor.
welcome.